So that's what we wound up doing here on the next page, was to make a sign chart for this guy, where we found those critical points by setting the numerator and denominator equal to 0. So that split up our number line like this. I looked at how those three factors, 9x plus 4, x minus 1, 3x to the 1/3, how those three factors change sign on each of those intervals. So aggregating all that sign change, we get negative on the interval from, in this case, negative infinity to negative 4/9. Positive on the interval from negative 4/9 to 0, so that then it's increasing there. Decreasing on the interval 0 to 1, and then increasing from 1 to infinity, right? So right here, we've gotten a bunch of information that we can collect from this first derivative. Namely, we've got the intervals where it's increasing. From negative 4/9 to 0, and from 1 to infinity. We have the intervals where it's decreasing, from negative infinity to negative 4/9, and from 0 to 1. Moreover, we have these other points where we know it's switching from decreasing to increasing, so that's going to be a local minimum. Or here, where it's switching from increasing to decreasing, so that'll be a local maximum. And then here we're going to have another local minimum. So there's going to be 2 points that are local minimum values, and then 1 point that's a local maximum value. So we have a local max at x equals 0, and we have a local min at x equals negative 4/9 and x equals 1. So just from that sign chart here, we've gathered all this information that we can use in our graph. If I want to be a little bit more particular, we can go through and actually evaluate the function at each of these points. And that'll give us maybe something a little bit more specific that we can plot on our graph. For now, I'll leave those for later, because I want to just now do the same thing, but with the second derivative. So now I want to analyze the second derivative. So let me remind myself what we got there for the second derivative. So it's 45x squared minus 10x plus 4 over 9x to the 4/3 when we had it all combined like that. Okay, let me double check that. Yeah. Okay. And actually, what I might notice here is that when I set the numerator equal to 0 to find my critical points, or actually, they wouldn't be critical points here, but because it's the second derivative, they would be points where I could have a possible inflection point. So when I set this equal to 0, maybe again here, I'll just try out the quadratic formula. And I can kind of tell just by looking at it, 100 minus, let's see, 4 times 45 times 4 will give me negative 620. So this is actually a complex number. So there's no real solution here. So that tells us that since this is never going to equal to 0, then we know 45x squared minus 10x plus 4 must always be positive. Okay, because here this shows you that it has no solution, no real solution. So it must be positive for all x. Okay, so that's helpful. Now we can just get the other point that we can consider is when the denominator equals to 0, which of course in this case is easier to solve just when x is 0. So my sign chart here will just have that one point, x equals 0. And the nice thing is we know that the numerator is always positive. And actually, because the denominator has this fourth power of 4, it's 4 over 3, but because it's the power of 4 there, it's like the cube root to the power of 4. We can think of that as also always being positive. So both of these factors will always be positive on either side here. So our second derivative will always be positive. So that tells us that the graph is always concave up on every interval here. So you see it's never concave down, and because it doesn't change sign anywhere, there's no inflection point. Okay. So actually what I might do is now we've gone through and we've analyzed the first and second derivative a little bit. Let's kind of put all those pieces together and think about what that tells us about the shape of our graph here. So let me kind of flip back to the previous slide for a second to remind us we've got these points, key points, -4/9, 0, 1. And it's going to be decreasing, increasing, decreasing, increasing. So we see that on this side here, we showed before that it was decreasing, and we know it's always going to be concave up. So it's decreasing and concave up, so I think the shape of the graph will look something like that. Between -4/9 and 0, it'll be increasing now, and it'll stay concave up. So increasing and concave up, so something like this maybe. From 0 to 1, now it's going to be decreasing, and it's going to stay concave up. So again, kind of more like it was here, right? And then here, increasing and concave up.
Is there a vertical asymptote at 0?
There is not a vertical asymptote because if we look at the original graph here, we can actually get a value 0, 0, right? We would get 0, 0 at the origin. So we actually get a value there. You can plug in 0 here and you get a point. So actually there's no vertical asymptote there, but we have, well, you can probably tell from the graph is that it would have to be like a hard corner, a cusp, because it goes from concave up and then starts decreasing but stays concave up. So it's going to create this little cusp in the graph there. And here, let's kind of And there's the same information there. Let's kind of look at what the graph might potentially look like. And here, actually, maybe I'll quickly just get those key points that we had. F of 0 is 0. F of 1 is, if I plug in 1 here, it's actually pretty easy to evaluate. Let's see, 9 minus 8 is negative, or is 1 minus 16 is negative 15. And then times 1 over 8. So negative 15 over 8. And then f of negative 4 over 9. Well, this one, maybe I need to punch that one into my calculator real quick to get an answer there. So let me just do that one just to get an approximate answer so we can get an idea of where to put the point on our graph. It's something around negative 0.77. Okay, so just getting a rough idea of where the graph might be at each of those key points. Actually, I'm going to kind of widen my x-axis a little bit. Okay, so we have those key points 0, 0, f of 1 and negative 15 over 8, so maybe something down here. Go a little bit deeper there. And then negative 4 over 9, so maybe somewhere in the middle here, and then negative 0.77, so somewhere around there. And yeah, we can kind of use the information there. We know it's going to be concave up over here, and then concave up over here. But notice here, it makes this interesting little cusp in the graph at 0, 0. So it's worth noting that here, this cusp is not smooth, right? So it's not differentiable there. So that kind of creates that weird hard corner there. So you see it's concave up on both of these intervals. It's got those local maximum and local minimum values that we said. So here's our local mins, and here's our local max. Okay, so let me just kind of look at what the book does. So it's kind of the same looking graph, but theirs is maybe a little better, but yeah, same idea. Notice that, yeah, we get the same basic shape here. Got a local max and our local minimum values, and we've got the basic shape here. So you see, even though I didn't go through all those steps for this example, I was able to gather almost all the information that I needed just from those first and second derivatives. Okay, so anyways, I'll leave it there for this section. I know it can be a little bit lengthy. Those problems tend to be a little bit long. So I don't want to we've already kind of spent a couple days working on it, so I don't want to, you know, get sucked into those problems. Because actually, the next section, I definitely want to spend a good amount of time going through optimization problems, which is another one of these sections, kind of like related rates, where you guys are going to need to read the problems very, very carefully, make sure you understand exactly what the problem is asking you to do, and then be very careful how you set it up. Okay, so I'm going to give you guys another warning here. Optimization is not an easy section. Okay, so you guys should expect these problems are going to be a little more challenging, but I'm going to show you guys how to approach it, and the way that you can approach it should work always. And the problem is that every problem is a little bit different. Every question has sort of a different little spin on it, and so you got to be able to interpret what we're asking you to do and piece together a function that you're trying to optimize. So these are skills that I think are really, really hard to develop, but they're going to be really important skills to develop. For instance, if you guys go on to become engineers, or you know, you work, you know, in some applied field, optimization is going to be a hugely important topic. Okay, so everything we're going to be talking about in this section is something you can apply in the real world. Okay, so even though this is going to be a really challenging section, it's going to be one of the most useful things that you'll learn in calculus. Okay. But again, I want to give you guys just a little bit of a warning that be prepared for this section. Be prepared to spend a lot of time working on 4.5. In other words, don't expect it to go really fast. It'll take some time to really make sense of it and get good at it. Okay, but here to kind of set it up, there's three things I want you to think about first. So generally, when we're given a problem, so optimization, okay, maybe you have an idea already of what this means. So say, for instance, you're running a business and you want to figure out how you can maximize the profit that your business makes. So what you do is you construct a function that tells you how much profit you make as a function of the price that you're setting for your items. So your variable here is price. And the function that tells you your profit is what you're trying to maximize. So then your goal would be to figure out, well, how can I set the price of my items in such a way that it will maximize my product or maximize my profit? Okay. So our goal here is to find optimal values. So, and optimal could mean different things. For instance, we want to maximize or minimize a function. Or actually, I'll say a quantity. For example, An optimal value that we might be looking for is one that maximizes profit. What would be one that you would want to minimize? Some quantity that you would want to minimize.
I'm not sure.
Say you're running a business. You spend money on certain items. So maybe you might want to minimize how much money you're spending. So you might want to minimize cost, right? That would be something where you want to optimize the amount of money you're spending by minimizing cost, right? Yeah, product cost. Yeah, good. So those are the kind of things we're going to be thinking about. Or, you know, maybe it's more of like an engine. So this would be from a business perspective. Maybe you're an engineer, and you want to say maximize efficiency. You're designing something and you want to make it as efficient as possible. So you want to maximize efficiency. So you come up with a function that tells you how efficient your thing that you're designing is, and then you want to adjust the variables in such a way to make it the most efficient that it can possibly be. Or maybe maybe you're designing a product and you want it to be cost effective, so you want to minimize the material used, the amount of material that's used. So again, this is maybe from more of like an engineering perspective. You're trying to maximize something to make your product better, or minimize something to make your product more cost efficient. Okay, so that's kind of how we're going to be approaching these problems, is there's always something that we're going to be trying to maximize or minimize. And the objective function is the function that we're trying to maximize or minimize. And the goal here, and so the problem is that oftentimes this function could depend on many variables. And in this course, we're focusing on the single variable calculus. So we want to come up with a function that depends on a single variable. And so that's where constraints come in. So constraints are restrictions on our variables that allow us to simplify our objective function into a function of a single variable. So if we can identify a function that we're trying to maximize or minimize, and then try and write that function as something that depends only on a single variable, well, then we have techniques for now finding the maximum or minimum value of that function. In fact, you know, that's what we've been doing this whole time, right? Finding the absolute max or absolute min of a function. And so the techniques that we've been using here can be used to optimize our function. So we can find the optimal values that will suit our needs. So with that in mind, let's just think about an example like this. So we've got a rancher who has 400 feet of fence for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions. What are the dimensions of the corral that maximize the enclosed area? And what is the area of that corral? So to visualize it, let's draw a simple picture here. You've got one side of our corral will be against a barn here. And then you've got the corral itself will be formed with sides going in between. So we've partitioned our corral into 3 sections. Okay. And by the way, we can just assume here that each of these are essentially equal. For us, I don't think that matters so much, but once we've kind of partitioned it out like this, now we see here we've got a corral, right, with three sections. So our goal here is we want to optimize the area we're using with a fixed amount of fencing. So we want to find the maximum area, but we're restricted in the amount of fencing that we can use. Okay, so let's put those 2 pieces together. So it's like now my objective function will be area, right? Because we're trying to maximize the area. So that means we're going to need to come up with an area function. So what might help here would be to introduce some variables. So notice that the barn itself has these 2 dimensions. You've got x for the length of these sides here. And then I'll make this the other side a y. So that would be the length of this side. Okay. What's the area of this barn? Or I'm sorry, what's the area of this corral, the whole corral? It's a rectangle, right? What's the area of a rectangle? Yeah, exactly, xy. Okay, so that'll be our objective function, xy. However, what we notice is it depends on an x variable and a y variable. So our goal now is we need to write this in terms of a single variable using our constraint. So the constraint, and again, the restriction on our variables will be the fact that we don't have an infinite amount of fencing to use. We only have 400 feet of fencing to use. So that's the constraint that we're working with. So we only have 400 feet of fencing. And so to kind of put this in terms of our variables, right, x being one side of our barn, y being the, or sorry, one side of our corral, y being the length of our corral. So how much fencing is going to be used here in terms of x and y? Because we've got, okay, we've got the fencing that goes down each of these partitions here, and then the fencing that goes along this edge here. So if I add up all these edges, we've got x, 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 and y, add them all up, that's how much fencing we're using altogether. So our constraint equation, we got 4x plus y is the total amount of fencing that we're using. And we know that has to equal to exactly 400. Okay, so this is telling us how much fencing. Okay, so now we've got a restriction on x and y that we can substitute into our area equation. Okay, so this constraint here, notice, we can combine this constraint equation with our area equation to get area as a single variable, area as a function of a single variable. Okay, so we can use this equation to substitute into the area equation. So I need to replace y with something. So I'm going to just solve for y here. Subtract the 4x. And now we have a function of a single variable. So area as a function of x now. Okay, so that's now the first, basically the first stage of this whole process is just coming up with the objective function now in terms of a single variable. So that's what we have here. So now we've got our objective function in terms of a single variable. Now we just rely on the techniques that we've done so far to find the maximum value of this function. Okay, so now our goal is to maximize area. So from here it's pretty simple. We find our critical points. Take the derivative will be 400 minus 8x. Set that equal to 0. And we notice here we just get one critical point at x equals 400 divided by 8. I think it's 25, right?
50.
50, okay. Yeah, 50, thank you. So there's our critical point. Notice this is the only critical point. So we know that this must be either our absolute max or absolute min. Of course, if we're visualizing this, it must be our absolute max because we have this upside down parabola. essentially we've just located the point that's at the top of the parabola. And by the way, this is now the dimension that will maximize, this is the x dimension that will maximize our area. So we also get the y dimension here by plugging back into our y equation. (400 minus 4 times 50), so I think that leaves me with 200. So those would be the dimensions that maximize area. X equals 50 and y equals 200. And then the second part is, what is the area of that corral? Well, then we can just find the area is 50 times 200, so 10,000 square feet. So that's the actual maximum area. Okay, so that what you guys notice here, maybe it's not quite obvious yet, but at least in this example, you can kind of see that by identifying these two things right off the bat, it helps us conceptualize and think about how we can piece the problem together. Here it was fairly straightforward because our objective function was just the area of a rectangle. And our constraint was just limiting the amount of fencing. So it was a simple equation, y equals 400 minus 4x, that we could substitute in. So combining those two pieces together gives us our function that we're going to then just apply the calculus techniques. We find our critical point. We know that must be where our maximum value occurs. And again, to help you visualize it, here's just a picture of the area, our area function, right? This is our 400x minus 4x squared, the area as a function of x. So we can see that based on different dimensions, you get different area. For instance, here, maybe if I had x was 20, then the area enclosed would be, something around there. Or if I had x was 60, the area would be something around there. But the one that's going to maximize the area will be when x is 50. Which gives me that barn where it's now, or the corral where it's now 50 on this side, 200 on this side. And so, okay, notice that, yeah, if we had other configurations, they would have smaller area enclosed. This is the one that's always going to give us, that we know is going to give us the maximum area enclosed. Okay. Let's try another example. Suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-based box with the greatest volume under these conditions? So notice that the first sentence, if I read that one again, suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. So right there, they're giving us a restriction on the dimensions of our box. They're giving us a restriction. So that first sentence is really giving us the constraint equation. And then what they're asking, what are the dimensions of the volume of a dimensions and volume of a square-based box with the greatest volume under these conditions? So what we're seeing there is we're actually looking to maximize the volume. So our objective will be, we want to maximize the volume. And our constraint will be that the sum of the length, width, and height does not exceed 64 inches. Now, another thing to keep in mind is that they're describing a square-based box. So the base of our box is a square. So when I'm drawing my box here, the base is a square. So these are the same dimension. Okay, so that's like the base here on the bottom is a square. But then the height could be a different dimension. Notice that it's not necessarily a perfect cube. So we're going to use a different variable then for the height, say y. So we've got a box where the dimensions are x by y. Can you guys tell me what is the volume of a box with dimensions x by y? Two xy, not quite, because xy would just give me the area of one of these faces of the box. So, well, here's just a reminder. If I have, maybe you guys never.
Would it be x squared times y?
Good, yeah, because in general, if I have, you know, just any rectangular box where it's x by y by z, you know, the volume, it will be x times y times z. So you just multiply the dimensions of the box together. But in this case, it's actually x by y. So it'll be x times y to get the volume. So the volume of our box will just be x squared y. Right. So, or here, let me kind of, instead of using x, y, z, say it this way. We know if I've got a box where it's got a length, it's got a width, and it's got a height. And the volume is length times width times height, okay? Easy. But in this case, yeah, because it's got a square base, the dimensions of the base are x by x, and the height is y, so x squared y. But again, we notice it depends on the y variable, so we want to try and write this in terms of a single variable. That's where our constraint comes in. So again, going back to that first sentence, it says that the sum of the length, width, and height cannot exceed 64. So the biggest it could be is 64. So then we're going to make sure that the the length, the width, and the height, so x, x, and y, sum up to 64. So I'm just going to equal it to 64 because we know that that'll give us the biggest that this sum could be. Since our goal is to maximize the volume, that's what we want, is this to be as big as possible. So in other words, we have length plus width is x plus y, or 2x plus y has to equal to 64. So that's our constraint equation. So again, what we want to do is combine our volume, our objective volume function with our constraint equation to get volume in terms of a single variable. So what I'll do is solve for y in terms of x here. And then I'll replace y in our volume equation to get volume in terms of a single variable. And here, let me just write that over here. Now we have the volume as a function of x. So we get 64 x squared minus 2x cubed. Generally, I should also, this is another thing that you guys might want to think about as well, is I should also think about what restrictions we have for x. Because x here could not be any real number. There is some restriction on what x could be. So not only is our constraint equation important to consider here, but we also know that x should be a positive value and y should be a positive value if we're talking about these being dimensions of this box, right? If y is a positive value, then we know 64 minus 2x should be a positive value. And then solving out here, we get x has to be, so 64 has to be greater than or equal to 2x. So x has to be less than or equal to 32. So with these restrictions here, we've got our x variable here is between 0 and 32. Okay, but with that in mind, let's consider that as we go. But now we can go through the process just like we did last time. We'll take the derivative, set it equal to 0. Here we get, let's see, 2 times 64, 128x minus 3 times 2 is 6x squared. Then I can equal that to 0. Find my critical points. So we get x is 0. Here, let me factor it. So we can factor out the x. And then I got 128 minus 6x. So we got x is 0. And let's see, 6x equals 128. So x is 128 over 6. Let me see what it's there. 64 over 3, I guess. So of course, I can assume here that if the dimension of our x variable is 0, that would not be the one that's going to give us the maximum volume, because actually notice that would give us a volume of 0. So instead, I'm going to use this as our critical point here. That one's not the right one. We can easily verify this as well just by considering on the interval 0 to 32, 64 over 3 would be somewhere around here, and then our volume, if we kind of check some test values here, you can try something that's less than 64 over 3. Plug it in here and you'll get a positive value. Try something that's bigger than 64 over 3 and plug it in here and you'll get a negative value. So it's increasing and decreasing. So we see that 64 over 3 is really our maximum on that interval 0 to 32. Okay, so coming back here to put the pieces together, we've got the dimensions that maximize the volume will be x is 64 over 3. And then plugging back into the y equals 64 minus 2x. I think we get the same thing, 64 over 3. So that means it's actually a cube, right? So okay, and then multiplying length times width times height, we get something around 9,709 inches cubed. So that would be our maximum volume. And these are the dimensions that maximize our volume. And in this case, notice it's a cubic graph, but here we can kind of see when I graph that function, it reaches that optimal value at 64 over 3, where the height there would be what we found, 9,709 approximately. Okay. So yeah, you notice that these problems can be a little bit lengthy, sort of putting the pieces together at the beginning at least. But actually what you'll notice is the actual work that we did here, once we get our objective function in terms of the single variable, is actually a pretty simple calculus problem. You just take the derivative and set it equal to 0. And we know that that must be where our maximum value occurs, since here we get that single critical point there on our interval from 0 to 32. So that must be where our maximum value occurs, hence the optimal solution there would be when x is 64/3. So, I mean, I don't know if I have time to do another example, but maybe we can just kind of think about the basic process that we've done in these last couple examples. And of course, this is how we should approach the problems in general. Start by reading the problem carefully, identifying the variables, organize the given information with a picture. Okay, so that's kind of how I started both of the previous examples. We start with a picture, label it with some variables. Okay, so that we can kind of see what the variables that we're working with are. And then the next step is to identify the objective function, in other words, the function that we're trying to maximize or minimize. Write it in terms of the variables that we've identified in the picture. So in terms of x and y, for instance. And then you want to identify the constraints. So what kind of restrictions do we have on those variables? And then put the constraint and the objective function together to get a function in terms of a single variable. So that would be the fourth step there. And then once we do that, then we can write the objective function expressed in terms of a single variable, find the interval of interest for that variable. So actually in the last example here, we expressed our v of x in terms of a single variable. Here was our interval of interest from 0 to 32, which basically was making sure that we always have positive dimensions. We don't want to have a box where the dimensions are negative numbers. And then once we've got the objective function in terms of a single variable, then we just use our calculus methods to take the derivative, set it equal to 0, to find our critical points, and then verify that whatever critical points we solve are either the maximum or minimum value that we're looking for. It might be necessary sometimes to check the endpoints, but in the last example, that was not necessary because we knew those would be the points where the volume would be 0.